Hello everyone, welcome to my channel. In this video I am going to solve a question from GATE 2016 which was asked for 4 marks. And now before starting to solve this question, we have to know a very important topic that is called Zimmermann-Traxler model. And this is very useful for you to find which type of enolate will give which type of isomer, like E isomer or Z isomer, like that. So let's start. Okay, first of all we have to know the model. And the question is, the favorable transition state leading to the formation of the product is in the following reaction is. Okay, you have given a structure like this, and these two reagents, that is benzaldehyde and minus 78 degree temperature, and in the second step H2O2 and NaOH. And you have given a product also. You have to find the favorable transition state. Okay, so there are the four options, this one, and this one. So you have to find probable or favorable transition state. So according to the question, you have to find the favorable transition state. So you have to know this model, that is Zimmermann-Traxler model. If you know this model, then you can easily answer it. You can easily get 2 marks in the GATE 2016. Okay, so let's start. You have to know Zimmermann-Traxler model. Okay, now see, this model says which kind of enolate will give which type of isomer. Now see, here is also give an enolate type of structure, and we have give a aldol type of condensation and aldol product. Okay, so for this question we have to know Zimmermann-Traxler model. So in this Zimmermann-Traxler model says that cis enolate will give syn aldol product. Okay, and the trans enolate will give anti aldol product. So these two are basic things, and after that we will move on the reaction type of transition state. Okay, now you have seen in the question that there is a trans enolate is given. Then according to this model, you have to the trans enolate will give anti-aldol product, and you can also see here there is a product given which is anti in nature. These two are anti just because of this is above bond and this is below bond, and so you can easily find, and you also get the same thing from this model. Now why this is important? This is important because of there is a different type of transition state this type of reaction follows actually. Okay, so now see, there is a structure like this. I am taking as an example. Okay, and this kind of see, I am taking this is aldehyde and this kind of enolate. And what type of enolate it is? It is syn. Why I am saying it's syn? This is because of this OLI bond and this methyl groups are syn to each other. That's why this is called cis enolate. Okay, now how the transition state occurs? This going to go here like this way. Okay, now if you write the structure like this way, Now see, there is a 6-membered cyclic transition state. 6-membered transition state. Now see, this type of cyclic transition state probably, or not probably, actually it is established, well established model, and this follows the 6-membered six-membered chair-like transition state. Okay, so we all know what is chair form or board form. We all know the concept of cyclohexane, so when we can easily tell that which conformer is chair and which is board. Okay, so this Zimmerman-Traxler model follows the cyclic chair-like transition state. Okay, now here I'm writing this way. This is X. Okay, this is your cyclic transition state. Now this methyl group is in axial, actually not axial. This is called, this position is called, specifically this position is called pseudoaxial. Okay, and this R group is in pseudo equatorial. Why I am saying this, it is pseudo and these two are pseudo, just because of these two positions are not in fixed axial or equatorial. That's why this is called pseudo, not actual, not axial or equatorial. But best position is this position is axial and this is equatorial. That's why this was saying as a pseudo axial or pseudo equatorial. Okay, and this is enolate, and there is another possibility, that is, there is another possibility I am writing here. Actually, there is another possibility, that is X hydrogen methyl okay, this is also another possible transition state, but this type of transition state, that is okay, this position, this R position is pseudo axial. Okay, now these two position, this two methyl and this R group and this X, one, I am numbering like this way, 1 2 3, this 3 position, 1 2 and 3. Now you see there is a 1 3 thin diaxial interaction. Okay, 1 3 thin diaxial interaction. So this is not favored as much like this, so this is disfavored process, or disfavored cyclic transition state, disfavored transition state. And this is the, there is also a 1 3 thin diaxial interaction, but this is not as much as here. So this is disfavored and this is the favored transition state, favored transition state. Okay, now see, after that there is a formation of product like this way. I'm writing here 6 and after hydrolysis H3 plus, this OLI bond gets protonated and form OH, and after that the final product is this. either these two positions are below or in above. Both the meanings are same, like this. Okay, now see, this is your syn product. This is your syn product. Okay, these two are syn just because of these two are same. These two have contain same stereochemistry, this OH and Me, and from where you can get that this from this cis enolate, cis type of enolate, you will from this cis enolate you get the syn product. Okay, this is also said that cis enolate will give syn aldol product. Okay, like this. And in case of, now see, I am writing this here. In case of trans enolate, now see what happens here. In the trans enolate, I am writing the same compound actually in this way. There is a X, okay, this is one structure, and there is another structure is also possible, that is this one. Okay, like that. But as the same thing happens in the cis enolate, there is also same thing happen in the trans enolate also, just because of there is 1 2 3, that is this kind of 1,3 syn diaxial interaction. So this type of cyclic transition state is not favored, so it is disfavored, and this is favored. Okay, so after that the same conditions, same thing is I can write like this way. Okay, like this, sorry, this is bond and this one. Okay, and after that, in presence of hydrolysis, in the presence of water and hydrolysis takes place, and this product is formed. This OH and this above is Me. So see, from the trans enolate you get the trans product. Okay, now there is a question, that is how I am writing like this way also, and this way this methyl is in equatorial, why not axial? Now see, these two Me and this R group, when, okay, I'm mistake here, no sir, not mistake, this methyl group and this R group, this methyl group and this two R group, in what position? They are, this methyl group also in equatorial position, whatever it may be, you may call it pseudo equatorial. So pseudo equatorial, this methyl group is in pseudo equatorial position, and this R group also in pseudo equatorial position. So if this, we know that 1, 2 isomer of cyclohexane, 1, 2 isomer, that when it calls cis, when that these two isomer, when these two 1 and 2 functional groups are in axial, one is axial and another is equatorial. But when this axial and equatorial, but when these two groups are, when these are, they are trans, when these two groups are either axial, either both are axial or both are equatorial. Now see, this methyl group and this R group, okay, this after it, this is kind of retro structure. This is not the direct structure from this one to this one. You have to rotate this bond. If you rotate this bond R group to the plane and this OLI or OH bond to this position, then is also the same thing occur here. Same thing also occur. So if these two bonds are equatorial, then these two are trans. These two are called trans. So in this type of structure, there is a methyl group in equatorial, and these are not actually this. After rotation, there is a OH. This methyl and OH groups are trans to each other. Now you can easily find out the trans enolate to trans product. Okay. Now see, there is another topic or another possibility also I am writing here, that is this R. I am writing a structure like this. If you add LDA in this compound, you get two types of isomer, this one and another is this one. Okay, so this is cis and this is trans. If the R group may vary, if the R group is varying, like if the R group is tertiary butyl group, that is large and bulky group, that's why this product is obtained in 98%, but this product is obtained in 2%. But if the R group is an ethyl group, then this is 30% and this is 70%. Now see why this type of percentage of product is occur. This is occurred just because of the this kind of this is because of the R group. And R group, this is tertiary butyl, then this is tertiary butyl, and this methyl group is, if this is tertiary butyl and this is methyl group is in the same site, so there is a large steric interaction present, then these two can not in same site, so it cannot rotate. Actually it can form this type of this synesis type of enolate, so not trans. Okay, so if then you get 98% of this product and 2% of this product. So there is if this is ethyl group, there is a interaction between these two is very much less compared to tertiary butyl group. So you can find this is as 70%. Okay, now cis enolate you can see here, and after that, if there is a given in the question, actually now come to the question. Now pH, okay, I am writing another example also, this one equal to this kind of structure, and not CHO and H2O2 NaOH. Now see, these two are trans, so if these two are trans enolate, so this is from trans enolate, then trans enolate, so what type of aldol product will occur? Trans type of aldol will occur to methyl. These two are trans. Okay, so there is another example. If the R group, this is CHX, so CHX means cyclohexyl. Okay, CHX is called cyclohexyl, that is in boron I have attached these two types of structure and these two type of bonds here. This is called cyclohexyl group. Okay, now after that, if you have no few things, that is if the oxygen is attached to boron, and there is another compound, this is not cyclohexyl. In this type of compound, I am writing the structure like this way. Okay, this type of structure is not too very bad type of structure. Okay, okay, now say this is called this is 9 bbn. So what is 9 bbn? 9 bbn called 9 bora bicyclonone. Okay, so it may look large, but this structure, it may look large, but it's not as large as well, but it's tied back to bond with boron from the behind. Okay, it's tied back. It's a very much strong term. It is tied back to boron from behind. Okay, now this is actually this from the same reagent, but you get this kind of structure. Okay, like this. Now see why this occurs, just because of this is not as large as the cyclohexyl group, and the cis enolate forms stereoselectively. This is called this is actually a stereoselective reaction. Stereoselective reaction. Okay, now in short you can write this is this CHX. If you have given this in presence of ET3N, you get anti-product always. But if you given BU2OTF like this in presence of ET3N, this is triethylamine, you get the cis product or syn product. Okay, like this way. Now there is one more thing, that this boron enolate aldol product gives the greater stereo specifically than lithium enolate. This is just because of this is probably due to the not actual surety, but this is probably due to boron and oxygen bond is shorter compared to lithium oxygen bond, and that is why the 6-membered ring is more tighter, and this follows the Zimmermann-Traxler model is very much effectively in case of boron and oxygen bond. Just because of we know when we going from lithium to boron from left to right on a periodic table, size get decreased. So compared to, from the lithium to boron, the lithium is higher compared to boron, and it can tightly bind with oxygen more. Okay, so that's why this type of different things which is occurred. So okay, I think I'm done all these things related to this Zimmermann-Traxler model. Okay, now let's come to the question. Now the question where said that this is a cyclohexyl group. Okay, I already told that what is CHX group and why this type of. Okay, now see, here is given this type of transenolate. So you know the transenolate form anti-aldol product. Okay, now see. Okay, now see, this is given to you. Now we can write, and there is I'm writing this way, pH. Now we can write this structure. We can write this in the Zimmermann-Traxler model, that is 6-member cyclic transition state, that is this way. So hydrogen, this is a methyl, and there is a boron and CHX actually. Okay, so see, there is one possibility, and there is also another possibility, that is this one. Sorry, this is not this type of bond, and this is oxygen, this is hydrogen, and this one is phenyl group, and this oxygen, and there is a boron, CHX. Okay, now see, there is a strong 1 2 3, that is 1 3 in diaxial interaction. So this, if this phenyl group is in upside, so it feels more stronger 1 3 in diaxial interaction, but in this case there is no 1 3 in diaxial interaction. A 1 3 interaction is actually present with this hydrogen, but this is not actually negligible or slow. It's much less compared to this one. Okay, so after that you get this type of structure. Now see, so you may find this type of, from this to this, this is 1 3 in diaxial. Now this, from this you get the trans product. Okay, but there is a given H2O to NaOH. So how this thing reacts with H2O to NaOH? We see the PaCHO, that is benzaldehyde, attacks with this thing, but this type of H2O to NaOH, how they attack, and we have to know the mechanism. I think we all know this mechanism, but I am also writing this mechanism. Suppose we draw on a structure like this way. I am taking as a hydrogen, these two are hydrogen, not this CHX. Okay, this is H2O to NaOH is given. Okay, so what is the structure of H2O2? Sorry, it's actually this way. You have OH minus, it can abstract the hydrogen from here and the negative charge over here. Now after that you have this O minus and OH. It can attack on the boron atom. Okay, if the attack occur in boron atom, then boron atom is negatively charged and this OH is okay. Now after that this bond will migrate to the oxygen and OH lived with OH minus, lived as OH minus. So after that there is, so then after that this is there is oxygen bond with pH2. Now after that the OH minus will attack on the boron atom, and this boron atom, if this negatively charged, and this is OH, and after that this bond breaks and you get your final product, that's OH. So here you can see this H2O2, how the H2O2 to NaOH will react with this boron cyclohexyl group. Then you can get this type of OH. And so I think I will cover all those topics related to this Zimmermann-Traxler model. Now let's find the options. So if the options is there is 1 2 3 4 options, you can easily rule out the 2 options which is given in the question, that is this one and this one, just because of this type of structure, this type of staggered formation is given. And but in case of this type of Newman projection which is given, but we know the structure, that is Zimmermann-Traxler model, the follow 6-member cyclic transition state. So this 2 cyclic transition state is given, that is one is this, another is this. So here we can see there is a strong interaction between these two because of this pH is in axial and this CHX group. And so this cannot be your option, just because of we seen that here this 1 3 in diaxial interaction present, so this cannot be your option. And so there is only option left, that is D. So this is your final option and correct option. Actually there is no interaction, just because of pH is in equatorial position and there is a boron cyclohexyl group, there is no interaction present, that is with hydrogen, which is quite smaller than this pH CHX and pH interaction. So okay, this is your final answer. Now I think I will cover all those concepts related to this topic, and if you find this video useful, and please subscribe to my channel. And okay, thank you for watching and have a great day.